So, what's the hardest working muscle in your body? No, it's not your legs, even during a marathon. It's that incredible engine in your chest that's been running nonstop since before you were even born. Today, we're going to dive deep into how that unstoppable machine, the human heart, actually works.
To get a real sense of its incredible workload, I want you to just think about this number for a second. 5 liters.
Yeah, 5 liters. That's how much blood your heart pumps through your entire body every single minute. It's just an astonishing feat of engineering. So the real question for this explainer is, how? How does this one organ manage such a demanding, non-stop job without your brain having to tell it what to do every second?
Okay, let's get right into it. The first and maybe the most important secret to the heart's independence is that it doesn't wait for instructions. It literally runs on its own unseen engine. This incredible ability has a name, and it's a fantastic one: autorhythmicity. It's kind of like automatic and rhythm mashed together, and that's exactly what it is. The heart muscle itself can create its own electrical impulse. It doesn't wait for a signal from the brain to beat. It generates its own spark. That right there is the key to its relentless consistency.
So, if the heart creates its own spark, how does that one little spark create a coordinated, powerful pump? Well, it turns out it follows a very, very specific path. Let's trace that journey through the heart's own internal wiring.
The whole journey begins in what's called the sinoatrial node, or you'll probably just hear it called the SA node. Think of this tiny little bunch of cells in the top right part of the heart as the boss. It's the heart's natural pacemaker, and it fires off about 70 to 80 impulses every minute. Every single heartbeat you've ever had, it started as a tiny spark right here.
So how does that spark create a perfectly timed beat? It follows this precise pathway. First, the SA node fires. That signal then zips across the upper chambers, the atria, telling them to contract. Then, the signal hits a critical checkpoint, the AB node, where it's actually held back for just a moment. After that intentional pause, the signal's released down into the powerful lower chambers, the ventricles, triggering that main powerful pumping action.
And that little pause I just mentioned, it's no accident. It is incredibly precise, and it lasts just this long.
0.16 seconds. It sounds like nothing, right? But this tiny delay is absolutely genius. It gives the top chambers just enough time to completely finish their squeeze and empty all their blood into the ventricles before the ventricles start their big squeeze. It's a masterpiece of timing that makes every single pump as efficient as possible.
Okay, so we've got the electrical signal down, but what about the muscle itself, the part that's doing all the heavy lifting? How does it handle this insane, relentless load without ever getting tired, like your leg muscles would after a long run?
Well, a huge piece of the puzzle is this really beautiful principle of physics at work inside the heart. It's a kind of built-in regulation, meaning the heart just automatically adjusts its own power. The more the muscle gets stretched by the blood coming into it, the more forcefully it contracts. This is known as the Frank-Starling law.
Honestly, the easiest way to picture this is with a rubber band. It's super intuitive, right? The further you pull it back, the more powerful the snap is when you let it go. The heart works the same way. When you exercise, for example, more blood comes back to the heart, which stretches the muscle fibers more. And in response, they automatically snap back with more force, pumping all that extra blood out, without you ever having to think about it.
But there's another absolutely critical reason the heart doesn't just burn out. After every single contraction, there's a brief, mandatory rest period. It's about a quarter of a second, where the muscle is completely unresponsive. You simply cannot stimulate it again. This built-in pause is called the refractory period.
And this built-in recharge time is non-negotiable. It makes it physically impossible for the heart to get a sustained cramp, something called tetanus. This mandatory pause is the heart's ultimate secret weapon against fatigue. It's why it can just keep going and going and going.
Okay, so let's put it all together. We've got a self-starting electrical system and a tireless, self-adjusting muscle. So now let's connect all these amazing parts to the heart's one and only job: creating blood flow. This entire sequence of events, from the start of one heartbeat all the way to the start of the next one, is called the cardiac cycle. For a typical resting heart rate, say 75 beats per minute, one full cycle takes less than a second, about 0.8 seconds to be precise.
And this whole cycle really just boils down to 2 simple phases. First, you have systole. Just think of it as the squeeze. This is when the ventricles contract and pump blood out to your lungs and the rest of your body. And then comes diastole.
That's the refill. This is when everything relaxes and the chambers fill back up with blood for the next beat. Squeeze, refill. Systole, diastole. I mean, that's the rhythm of life right there.
Now, when you measure the total amount of blood that gets pumped out by each ventricle over 1 full minute, you get a value called cardiac output. And this brings us right back to where we started. For the average adult just chilling out, that value is, you guessed it, about 5 liters per minute.
You know, what's so amazing is that all this complicated machinery buzzing away inside our chests actually produces external signs that we can easily measure. We call them our vital signs, and they're like a direct readout from the heart's control panel.
For instance, when you check your pulse at your wrist or your neck, what are you actually feeling? You're feeling a pressure wave. It's the rhythmic stretching of your artery walls as that surge of blood gets pushed out from the heart during the squeeze. And that's exactly why your pulse rate is a perfect match for your heart rate.
And then, of course, there's blood pressure. We've all seen those numbers pop up on a machine at the doctor's office. You know, something like 120/80. But what do those numbers actually mean?
Well, these numbers are a perfect little snapshot of that cardiac cycle we were just talking about. The top number, the systolic pressure, that's the peak pressure in your arteries right at the moment of the squeeze. And the bottom number, the diastolic pressure, that's the lowest pressure in your arteries while the heart is in its refill phase. So that simple reading tells you the exact range of force your system is under with every single beat.
And all of this brings us to one last really interesting question. We've seen that the heart is autorhythmic, that it has its own pacemaker, that it can pretty much run all by itself. So, if the heart's electrical system is so perfectly self-sufficient, then why are there even nerves connected to it? Well, that's a hint that while the engine can run on its own just fine, something else is needed to hit the accelerator or apply the brakes.